Okay. So I will stop talking and giving the floor to John Reisman.
Thank you. The larger role of climate communications needs a bit of context. Of course, first in science, there's modeling and data collection and physics and mathematics, but then it comes to interpretation and interpreting what it means to public and policymakers. But beyond that, we have a lot of complexities in climate communication, so getting to what it means to society is very important. To do that, we want to look at system science. One of the most elegant theories in system science is living systems theory, but it's largely too complex, so we're going to look at it from a general systems perspective and simplify it. All systems generally have parent systems, subsystems. Subsystems are collateral systems to each other, and they can have subsystems as well. You look at this from the macro to the micro. The dynamics are generally centrifugal, centripetal, and dynamic equilibrium. In the climate context, you could look at the radiative forcing equilibrium over the Holocene, and then base, what's that baseline against what we're doing today. And it really, it's just inward, outward, and balancing forces. The Earth is a system. If you think about our system, we have collateral systems, they're planets. Our solar system is our parent system. And in that context, we're aware, of course, that the Milankovitch cycles cause orbital forcing along with precession and obliquity that actually get us in and out of ice ages. In the Earth system, we have a lot of teleconnections between the atmosphere, the land, the water, of course, the solar energy we receive from the sun. So it's important to understand those teleconnections. The dynamics generally in systems are protectionary or evolutionary, and these can cause conflicts at boundary layers. They can also cause, when they're interacting with systems around them, synthesis. There's commensal systems, parasitic systems, and of course all interacting constantly. They're also interdynamic and multidirectional. So when an event happens, the magnitude or resonance of that event can actually kind of go through the entire system like a mobile. When you shake one part of a mobile that's hanging in the air, and the magnitude, of course, it depends on the system and the actual event and the type of system you're looking at. When you look at a picture of systems, you can say, well, what is it? And that actually can be anything. That could be a giant corporation with multiple divisions in several countries and departments and offices. It could be a government system. It could be a meta system. It could be a psychological system, a belief system, how the brain functions, how the human body functions. So systems are just these dynamic components that interact with each other, parent, sub, and collateral. The four basic systems on Earth, earth, wind, fire, and water. Earth has mineral systems, chemical systems, tectonic systems. The atmosphere has, of course, the Hadley cell, Ferrel cell, the polar cell, jet streams. Our fire, I use the sun as the image of our fire because we get most of our energy from the sun, a little bit from a molten core. But if you think about it, in this context, when you turn on your car, you're turning on the actual energy of the sun every time you turn on your car because you're burning fossil fuels, and that's solar energy that was stored millions of years ago that we dug up and started burning. So we're actually using the sun in our cars and our airplanes. The water system, cryosphere, of course, freshwater systems and the oceanic systems all have their own subsystems as well.
Thermal equilibrium for the last 10,000 years is shown as 0 watts per meter squared. Ice age is around -6. For the past million years, the natural cycle has oscillated between warm periods and ice ages. Milankovitch cycles initiate these natural changes. Changes in the distribution of sunlight alter seasons, greenhouse gas concentration, ice cover, and ocean temperature. Lately, natural cycle produces a warm period about every 100,000 years. We came out of the last ice age 10,000 years ago. In the natural cycle, Earth should gradually cool, descending ultimately into another ice age thousands of years from now. Instead, we are warming. Increased greenhouse gas concentrations have increased climate forcing. Total positive forcing is estimated around 3.6 watts per meter squared above thermal equilibrium, higher than it has been for millions of years. The climate system has left the path of natural cycle. We are warming, and the warming is accelerating.
So we look at this from an equilibrium standpoint of where we were over the Holocene to where we are now. We've seen the natural cycle over the last million years and oscillating in and out of ice ages. We need to know what this change in the system does in our subsystems and collateral systems on the planet. So when we look at our planetary systems, we're looking at our atmosphere interacting, warming up because of greenhouse gases. We're losing the polar ice cap, probably within, certainly within 30 years by base estimates, and possibly within 10 or 15 years. That causes a polar amplification effect, which we're already seeing as the albedo changes now. The extra heat in the atmosphere warming up the oceans, causing stronger tropical cyclones and hurricanes, and also as a positive feedback with the H2O cycle. CO2 absorption affecting plankton life and changing the ocean acidification, the pH balance, and how that interacts with the vegetation on our planetary system, because the vegetation relates to the carbon sink and, of course, us, our food system. When we're looking at how that interacts, we have a latitudinal shift we've already seen in the data. The croplands are in yellow, and the brown spots are actually the drought events over a couple of years. And as they aggregate, we can see that along with the latitudinal shift, it's starting to impose itself more and more onto the croplands. So from the subsystem food perspective, we need to pay attention to that and what it means in the future. Wildfires, this is just from America, actually, US wildland fires, and doesn't have climate attribution. However, it's a good piece of data, and it seems to be following a trend, and you mix it with all the other pieces of data till you figure out what's what. Not a climate-related issue generally, but sort of because of climate shift, latitudinal shift, but we're actually depleting our aquifers in an unsustainable manner. They're not replenishing. This is a subsystem that needs to be in context of climate change as well, because we're moving where the water falls. Hurricane intensity, of course, increasing. Number of named storms per year increasing. Soil moisture content, interesting because we see drier areas in soil moisture content. We also see wetter areas. So in different ways at different times, you can have droughts in one area and a flood wiping out a crop in another. So we're having problems. We need to know what that means, not just now, but also as the trends continue, because we have a lot of radiative forcing in the system now. Net primary production throughout the 80s and 90s went up about 6%. And when the NASA scientists looked at it again this year, they thought they were going to see probably something similar. This just came out about a month ago. And what they found is that we had a 1% decrease. So it's most likely part natural variation and part climate signal. But we need to have that in context, because where we thought we were going to have more growth probably for a longer time, now we're seeing that that might not be the case. So that's another important consideration, especially regarding food. Understanding our economy. First of all, our main economy is our resource economy, minerals, chemicals in the soil. We use that in our manufacturing processes. Regarding the food system, of course, wheat, oats, barley, corn. The monetary economy is a meta-economy because we use money as an exchange to help trade resources. So it's an important consideration because it's going to be affected by resource changes in our use of the resources and also how climate change affects our resource system. We're currently operating mainly around the planet on the Keynesian economic model. That requires growth. For growth to be sustainable, it's difficult because we're doing a lot of changes to the infrastructure we built during the Holocene. So we need to get that into context as well. The main economic teleconnections: agriculture, latitudinal regional shift, aquifers and droughts, soil moisture content changes. Interesting issues in bees. We see bees dying off. We don't know exactly why. They're working on the attribution there. The Roundup issue has to do with pesticides. This was from the company Monsanto, and it actually helped us produce more crops, but now we see insects adapting to that, and that could be a bigger issue, because if the insects aren't able to be handled or managed, that will affect our food system as well. Ocean acidification issues, system degradation rates. We have to start thinking in timescales, short, medium, and long. Human migration and conflict, kind of going along with latitudinal regional shift and resource scarcity. Infrastructure shift. Once again, all of our infrastructure was generally built up throughout the Holocene, 10,000 years. So we've picked our places to live based on the relatively stable climate, even with natural variation, of the last 10,000 years. Now, inside our economy, I add climate communication and climate policy because even though they're meta-systems, they're attached to all these other issues if you look through time, and short, medium, and long. If we can get science connected better to policy and have policy that is more science-based, then we have a better chance at mitigation to come up with policies that work for our global economy and our global systems. The Department of Defense has weighed in. Climate change could have significant geopolitical impacts around the world. The CIA has also had a comment. Global warming becoming a greater concern, and they're considering big picture. They're looking at vegetation, they're looking at overgrazing, deforestation, soil depletion, all sorts of issues. What does that mean to global security? The Center for Strategic and International Studies, this was actually during the Bush administration. Former CIA Director Woolsey was the CIA Director under George Herbert Walker Bush. Their assessment came up with, at 1.3 Celsius, heightened cross-border tensions, large-scale migrations, resource scarcity, increased disease proliferation, economic consequences, some geopolitical reordering. And this is a model of what might happen. They're trying to figure out, all right, what might it look like? At 2.6 Celsius, massive societal events, pandemic disease, coastal flooding, armed conflict over resources, nuclear war is now possible. Now they're talking about nuclear war because this is a security group that works for the Pentagon. So they're looking at things in global security issues regarding the military. 5.6, this is the catastrophic scenario. MIT did a report in 2009, combined analysis of science and policy. Probability of surface warming based on our current policy, business as usual, 3.5 Celsius to 7.4 Celsius, with a 90% probability of falling within that range. The mean of that range is 5.2 Celsius, very close into the catastrophic range. Things that we need to consider regarding policy in our communications. The confluence issues include all of these, of course, economy, energy, and environment. Bob Carell did an analysis in the spring before COP15. That analysis revealed that if you added up all the agreements by all the nations, we still end up with a 700 part per million CO2 world by 2100, with, based on the current sensitivity analysis, 4.5 C. We're already at 389 parts per million, and we know CO2 has a lag time because of its atmospheric lag time and the amount of time it takes to absorb into the oceans. So we're looking at a warmer world. It's hard to imagine how 700 parts per million can be tenable in policy consideration. So we need to start assimilating what that means. A couple of major policy considerations: cap and trade. It's a carbon trading mechanism that provides methods to buy and sell carbon output. It can be effective, but it may be too slow because that's what they were using for their policy considerations at COP15, and it still added up to 700 parts per million. Fee and dividend is looked at as an approach that's more simple, revenue neutral, by the mechanism by which it wants to operate, to pace emissions and move us into, of course, a sustainable economy with renewables. Transitioning to this new economy or energy economy is very important, the speed of which has to be regulated by our economic needs, as well as, of course, our reality regarding the climate. Climate communications needs to be considerate of system resonance, scientific observations, impact potentials, system interdynamics. What climate change means in physical society, especially economic systems, and of course time. How fast will things happen and how will that impact us? So the role of communications, the larger role I see as trying to get the science and the policy together so that we have really informed policy, because this is critical. We are the human subsystem on this planet, and we rely on all these other subsystems to be functioning, to not have too much conflict. So in summary, to achieve a policy that protects our economy, our resources, and in fact us on this living system, planet Earth, that we call home together. Thank you.